New in version 4. It's kind of tight of time, so I will start directly with that. And version 4 came a month or so ago. I don't remember, it's 2 months ago. And one of the key features is that we have improved the built-in libraries. So we have added several libraries from these Mathematica standard libraries, where I show there were mechanical components and so on, including libraries for where also the existing libraries, like the rotational library and translational library, we have added capabilities to model the thermal properties of those systems. And a fundamental wave library, which is basically the old J omega method in order to make faster simulations of electrical machines and so on. So this means that with these extended libraries, you can develop more systems just out of the box than you could do before. But I will not really show details there, because the more interesting addition is the SystemModeler library store, which I will spend quite some time on. So with SystemModeler 4, we developed a system to add licensed libraries in a streamlined way. So it's easy to install additional libraries. And that you do from the library store. And as I mentioned it says Mexico here for some reason. That's probably because it's a Mexican that has developed this model plug library. Anyway, today we launched this model plug library. So it's a library for connecting actually to Arduino. So as you asked for robots, I think actually this has a small, even though you asked for some other type of robot, I imagine. This is an example for how you would use the model plug library, where you have in SystemModeler you build up a system with a control panel, a robot arm, and then some filters here to get a smoother drive of the system. And at the end, what you will have is a system where you connect a simulation model with a robot arm. So you have an input from the control panel, goes to the simulation, returns to the robot arm. And if we look at that in a it will look something like this. So you will have a connection where you use the model, and you have the library complete drag and drop, built this together to connect to the Arduino board and communicate with the system. So you don't have to do any programming at all. You just use a drag and drop library, just as it was with the hydraulic library or the mechanical library and so on, and then plug in your Arduino board, and it kind of runs. That came today, so I don't have a slide prepared for that, so that was kind of extra information, but the connectivity session will discuss more about that. But one important thing that we added is the hydraulic library. So the hydraulic library applies, of course, to a lot of different domains. Heavy equipment is probably one of those where you would most likely think of. Aircraft, automotive, robotics, and so on, are all systems that are heavily dependent on hydraulic systems. The library contains components of valves, cylinders, and so on. So if I look at that, there we go. If I look at the library, it has, you already saw an example, it has different valves. I can open valves and see the directional control valves of different types, like conventional solenoid actuation valves, and so on, proportional actuated valves, and so on. So we have all these different components, and you can use those to build up a system like a cylinder motion system. So if we look at the hydraulic library system, it will look like this, where we have a pump here, which was driving at a constant speed, and that is basically driving a valve, and depending on how it goes to a valve, and depending on how we control the valve with the input signals there, it will either be in different positions where we will do different operations. And we have a pressure relief valve and so on. And at the end, what we activate here is a mass that we try to move forth and back. So when you have this kind of system, it works just the same way as any other system modeler model, that I simulate that, and I have access to all the components, like the position sensor, so I can look at open the position sensor and see the position of the mass, how that is moving. Or I can access, let's say, go to look at the load position, oh, that was the same, the load speed. Or I can go into any of the tanks, look at the pressure. Well, that was boring. Oh, the tank, of course, will have a constant pressure in this case. But I can go to pressure relief valve and look at the leakage, pressure, mass flow, and so on and so forth. So I have access to all these variables, and I can connect it, as you saw, to other systems. We also added a smart cooling library. This, just as a hydraulic library, is a commercial library, a paid library that you have to pay extra for. But this is used to model cooling system, especially in automotive applications. So if you want to model, for instance, cooling fans or water pumps, these are included in this library. And this library, by the way, is developed by a third party, Austrian Institute of Technology. So if you're interested in developing and deploying your own libraries, you can do that through the library store now. And they will be, and users will be able to buy them, or if you provide it for free, to download them for free, and then install them automatically to SystemModeler. A library that was available from before, so I will not really go into that, is the Biochem library. This model here, we have the Biochem library. Basically enables you to do, let's show a very simple example first. Simple pathways that are Biochem examples. This is the simplest possible biochemical pathway. 2 compounds, glucose 6-phosphate, or however that is pronounced in English, and fructose 6-phosphate, that are connected with some reaction here that has some kind of parameters that governs the reaction. And basically what we simulated here is the transfer from one to the other, and basically the mass balance between these two. And as you go, you will develop more complicated, more complex systems like the metabolic system, which has a lot of these compounds. And you can also then add, so in these we have the liver, we have the cardiovascular system, and we have the blood plasma. And each of those have those kind of pathways that are interconnected to each other. And we can do experiments. In this case, we have insulin that we inject, and we want to see how insulin transfers through the body. And we can get something like this, where we will see a variation. We do simulation with different inputs, and we'll get different outputs on the level of insulin in different parts of the body. But you can also do, and as I saw this, I hadn't planned this, but this is actually an interesting new feature of SystemModeler, where you can, I should play it, where you can see dynamic diagrams. So this is when you combine Mathematica and SystemModeler now. The diagram that you saw, this is the diagram as the drag and dropped in SystemModeler, but we have added now from Mathematica. In Mathematica, you can automatically get these kind of arrows here that show the flow of insulin, in this case, in between different compartments as the simulation goes on. And it's 2 different simulations, one from a healthy patient and one from someone with a disease. So if I repeat that, you can see we are entering the infusion there in the beginning, and we can compare how these two behave differently. So now we can use this to understand how a healthy patient is transporting insulin compared to non-diseased or a diseased patient. And if I have time, I might show a little bit larger example later on. There's a planar mechanics library also added, which is, yes, as a biochem, it's a free library. You can download that. It's primarily for didactical purposes. So for education, you can use that to do things like a Newton's cradle or similar things. The wheel that I showed in the previous presentation was done with the planar mechanics library. So that's one example. And if you're especially interested in a topic, just stop me and I'll just, as I did with the biochem, I'll give a little bit of extra explanation around that. There's a system dynamics library, which is used for systems that I would say are quite different from the rest of the systems that are typically developed in SystemModeler. It could be things like developing a system of an energy market or a market to see how do we best meet demand depending on which supply we have of a raw material. How would we use that to meet demand and maximize our profit? Or it could be more logistic to see how do we transport oil from A to B in the most efficient manner. It could be disease propagation. That might be interesting today with Ebola, so like an influenza epidemic, where you would see things like this, where you can study how an influenza outbreak. You have the green curve here is the non-infected population. In the beginning, no one is infected. Then after a while, they start to get infected. And I was there like 2 weeks ago. I started to get here. And then you get sick, or some of us get sick. And then after a while, you get healthy. And this is like 1 or 2 days ago. I entered to the healthy population again. So in this way, you can use the model to study what happens if we try to stop the influenza from spreading in this occasion or that part. How can we best prevent an epidemic or even more a pandemic situation? So that's the kind of things you do with the system dynamics library. We have added a lot of help in the help system has been vastly improved. So we added a documentation center where everything is gathered together. So for instance, if you want to get started, you click on Get Started, and it looks similar to Mathematica's documentation center, where you will have introductory videos, tutorials, and so on. And if we go to the question of how are the components documented, then we can go in, let's say, to the mechanical system here, look at the rotational library, and each library has the documentation like this, where you can find, let's look at a component like an inertia here. If I click on that, I will get a list of different features that I could look at. For instance, I can see examples in which it's used in order to understand the uses of it. So it automatically lists all examples where it's used, and I can click into that example, learn more of how is this example set up, what are the results. I can open the example, simulate the example, and try it that way. So everything is cross-linked and put together in ways so you can go from either start from an example and find the different components, or if you start from a component, find examples that correspond to that will show you how to use it. This is also available from reference.wolfram.com, so you can see the whole documentation from there and look at it. And that goes for the built-in libraries and everything else too. I will not talk too much about this, as there is a separate session for that. Connectivity and deployment is a really important part that we added to SystemModeler, and that's why it has a separate session. But basically, it's a way to do things like connecting input devices. So sometimes I'm bringing a quadricopter with me, or a gamepad, and then I have a quadricopter that is modeled in the simulation center, and I use the gamepad, and I can control it and drive the simulation from that. So that's one thing you might want to do. Another thing is going the other way around when you want to drive a physical system from the model then you can do that, for instance, by TCP-based communication, which is standardized and set. And there's also added something called functional mockup interface, which is a way to export your models. So once you have the model in SystemModeler and you want to use it in some other hardware or software, you can export that in the so-called functional mockup unit, which is a standard and is used by 30, 40, 50 other tools. So you can import into them, like for instance, NI-Varistand, and try real-time, develop it for real-time applications and so on. But there is a separate, as I said, a separate presentation of that. Another thing, you asked for how to get the equations into Mathematica. I will show the other way around first, because we added that to SystemModeler 4. So we have improved the integration to Mathematica a lot. So things are much smoother, it's quicker to do things. But one of the things is that we made it possible to create models from Mathematica. So if we look at this system here, so Mathematica, let's zoom in. In Mathematica, you can define state space system and transfer systems like this. And then we added a function create model that takes the Mathematica system and creates the corresponding model with the name you give it. So if I press Shift Enter here, what will happen is that this is created, and if I go to SystemModeler, I can now reuse this system within SystemModeler like this. Kind of doesn't make any sense to use this probably in the biochem pathway here. But in that way, I can start creating my own components from Mathematica. It could be based on equations also. So I could say, like creating a bouncing ball model with typical Mathematica equations, adding events, setting initial equations and so on. And I can create that, and I can either, I will get that up here, what was the name? Bouncing ball. I get that to my model here, but I can also simulate that from within Mathematica just as any other simulation or model. But more, I would say more importantly, what you can do is from within Mathematica, rather than using the graphical drag and drop way to connect, sometimes it makes sense to programmatically create your models. And now you can use WFM Connect components to do connections. So we'll create something called apps sign here. And we have a list of components. One component called A, which is of the class apps. One sign, which is of the class sign. And these classes are Modelica classes from the libraries within the Modelica standard library. And then we say some connections that we want to connect sign.y with a.u. That's the two things we want to do when we create this model. So, yeah, so this is Mathematica command. And you might wonder with this simple example, why would I like to do this? Okay, this would have been faster to connect in the graphical user interface, of course, right? But suppose you have a system, let's say you have an electrical system where you have different types of electrical resistors with different behaviors, like faulty behaviors and so on. And you want to build a huge set of different models where you will use this faulty resistor in different combinations at different places. Then you can generate all these programmatically to get a table of models from within Mathematica rather than to having to connect each and every one of them by hand. So you can get a huge amount of models that you can simulate and then test the behavior. No, I don't think so, but I actually don't know. Yuan? No? Does it work on the reps? Yeah. Yeah. So you asked about also how do I get equations into Mathematica. So there is a function here. We can query the model for there was WSN model data, I guess, rather. So I went to the help. So the help from within Mathematica is the same, works the same way as any other Mathematica help, of course. So I have the different functions here, and I can find WSN model data. And from WSN model data, I can query things like, give me the diagram. There should be an example of system equations here, I guess. Yeah. So you ask for the model name and system equations, and you will get those into Mathematica. And then you can start manipulating this in Mathematica. There are several examples online where you can download examples and try it out. Where I download that? I don't have that prepared, but we can look at that afterwards if you like. Yeah, because I kind of 2 minutes left, I think. Don't say that. So, what is new? This is a very fast go through it, like a selection of what's new, and try to lift it up to a higher level. The first is expanding the scope, so adding both built-in libraries. I didn't really show examples of that, but digital library, closed stationary library, additional functionality to the rotational, translational library, and so on. I focus quite a lot on this, new add-on libraries that you can add functionality, among those the hydraulic library. There are also things in the way that you can easier get started with it by adding the documentation center. Yet again, very quick go through it, but it's a very important way to kind of gather things together in a more structured way than in the previous version. There's also a lot of small improvements in Model Center and Simulation Center to make it easier. For instance, how to structure parameters and so on. Connectivity, that will be a separate presentation of that. I'll get back to those in the last slide. And finally, a lot deeper integration with Mathematica, where I quickly, for instance, showed the dynamic diagrams, which perhaps would be easier to see on that where you have tanks with levels that go up and down rather than looking at a plot. There are the programmatic creation of models. But also, we have made sure that it's easier to use other built-in functionality within Mathematica that was available since previous version, including Mathematica 10, like using the gauges to visualize your system, to make that more direct. There's enhanced control system capabilities in Mathematica, and we'll also make that easier to use together with SystemModeler and so on.